Very good morning to everyone. Today we have a master class which will be taken by Mr. Radhakrishnan.T. I would like to briefly introduce him to the participants. He is working as an assistant professor in the Digital University Kerala, formerly known as IIITM-K. He works in the area of geospatial analytics. He holds master degree in geography and M.Tech in remote sensing. His key teaching and research areas include geoinformatics, geospatial technology applications, remote sensing, spatial data analytics, data modeling, spatial statistics, WebGIS mapping, and geospatial surveying. He had worked in industries prior to joining IIT-M-K in 2006. He has served as the project investigators in several geospatial technology projects funded by various organizations, mostly from Government of India and Government of Kerala. He has conducted over 40 training and capacity building programs in geoinformatics related areas. He has guided academic projects in BTech, MTech, and MCA. And he has set up an advanced state-of-art geoinformatics laboratory in his institute. He has served as a key resource person to over a dozen of workshops during last 2 years. I'm very thankful to you, sir, that you have agreed to listen to our students today. I hope that your lecture will be enlightening for all the participants. Over to you, sir.
Thank you so much, Dr. Kasuri. Good morning, dear students and faculty members. At the outset, I thank the organizer, Dr. Kasuri Mukherjee, for giving this opportunity to talk to you. As she was mentioning, I'm heading the Geospatial Analytics Division in IIITM-K. Apart from doing the academic activities, we are also into taking up projects for the government, basically with societal relevance, the projects with societal relevance. Currently, we have ongoing 10 projects. We have completed some 22 projects until last year. And this year, we have got almost 10 projects from various state government departments, and one research project funded by Ministry of Earth Sciences. So I think we will start today's session. Let me share the screen. Can you see my screen?
Yes, sir. We can see the Zoom link meeting.
Yeah.
Yeah. Okay.
Yeah. So before going into the presentation, this topic is on geostatistical analysis, basically Kriging. Before we go into the concepts and techniques of Kriging, we will just start with the use case where it is applied and what is the relevance of this. So we'll start with the use case and then come back to the presentation. Now, this is a QGIS interface, and we have some data belonging to a panchayat in Kerala. By the way, this area is important in many aspects. Like this is the middle part of the Kerala. This is a coastal tract. This extensive rice cultivation is there. It's also known as the rice granary of Kerala, which also happens to be the Ramsar site, wetland site, because this particular region, the land is little below mean sea level, almost 60 centimeters below mean sea level. And previously, this was openly connected with the lake, which you see here. It was connected to the lake. There was a natural flushing. Whenever there is monsoon, this area gets flooded, and after that, the water recedes to the lake. And when there is a high tide, water from the inland lake gushes into the paddy fields, and the cyclic movement of water was there. And in late 70s, a bund was constructed. It's called Tannirmukam Bund. After constructing that bund, the natural movement of the water is arrested. So we have a lot of environmental problems and related agricultural problems. And we have some data collected from the field. Actually, this data is collected by Soil Survey Department. What they do, they go to each tract of land and they collect the soil sample, along with they collect the GPS coordinate, and they bring the sample to their lab and do the analysis and prepare this data. So the problem which we are going to discuss is, now if you zoom in and see the points, you can see that the points are collected, or the samples are collected from random locations. In reality, this is how it happens. You cannot have a regular grid-based sampling from the field. Otherwise, it is an experimental site. In the open land, it is an extensive land. You cannot manage to collect the samples at regular intervals. Now the question comes: you have a lot of areas where we don't have samples. So there are a lot of unsampled areas, and we all know that this is actually is a typical statistical concept. You are collecting samples. From the samples you are estimating to the whole area. In classical statistics, we do the same thing. From the statistics, we estimate to the population. So in this case, the samples are sample locations, and the population is the entire study area. So you want to estimate. Otherwise, if you don't do it, you cannot use it for any planning, because you need a continuous, what we call as seamless data of the variable, whatever the variable may be. Only then you will be able to do some planning. So this is just a case of soil nutrient, and similar to this, you have a lot of contexts where you wish to take sample locations from the field and do the estimation for your study area, such as pollution, water quality, all those aspects. So this is the context in which we are going to have the presentation. And you may think that if you're not introduced to Kriging before, you may think that what is exciting in this, what is thrilling in this, because you can take the distance, you can measure the distance and do the averaging. But that's not possible in reality. Why? Because in this case, we are taking soil nutrients. So these are all soil pH values, Now, in place of this, assume that you are taking some other aspect, say, for example, water quality, the contamination, water contamination, or air pollution. So do you think that all these variables will tend to behave the same way in the Earth's surface? No, because there will be a lot of factors which influence the spatial variation. It will be different for different variables. It will be different for soil nutrient, it will be different for water quality. You cannot take the average and estimate a value in between in an unsampled location. So there will be a lot of factors. There will be a lot of the laws of physics will influence this. So you cannot standardize with a mathematical averaging. So you need some alternative methods to accurately estimate. So our question in hand, our problem in hand is, with the limited samples or sparse samples, limited samples, how best we can estimate or how best we can predict the variable in an unsampled location in a seamless way, so that you can utilize this for the planning purposes. So with this, we will move on to the presentation. My idea is that after discussing some of the concepts, I'll give a demonstration how we can do it in QGIS and how we can do it in R. I had a quick look of your syllabus. I came to know that you have R in your syllabus, but I'm not sure which semester of students are there. Have they already introduced? I'm not sure. Dr. Kasuri, have they already started learning?
Not everyone. Not everyone.
Oh.
A few of them, yeah, already started. Yeah.
Fine. So So we'll start with defining a geographical variable. So geographical variables are quantitative or descriptive measurements of various geographical characteristics collected from specific locations. Examples: species distribution, biodiversity measures, soil properties and types, plant species, climatic variables, water quality, crime, accidents. So many a times we would like to do this spatial interpolation. So spatial interpolation is most of these phenomena are normally measured from random point location. See, in earth science or environmental science, we have to have samples. We cannot collect data from everywhere, considering the time factor as well as the cost factor. So we have to live with the samples. So how many samples required for a particular analysis, and from where will you collect the samples? What is the spatial distribution of samples is altogether a different discussion point. That depends on the type of variable as well as the nature of analysis you are going to do. Suppose if you want to do say a density mapping or kernel density estimation or quadrat analysis, or nearest neighbor analysis. So these are part of point pattern analysis. It's called PPA, point pattern analysis. Here we are going to discuss about interpolation of the attributes collected from defined locations. In any case, spatial interpolation, or sometimes it's called spatial prediction, is a procedure of predicting the values of geographic variable at ensemble locations from measurements made at known locations. So suppose if you have this, the diagram on the left side is the input data. You have certain process, you apply some process or techniques, and you will get this output. You will get a seamless pattern of how the nutrient or the particular variable is varying in space. So all you require is this input data should be in the form of XYZ. It should have latitude, longitude, as well as the variable value. So normally when you say interpolation, there are two types of interpolation: deterministic method and geostatistical method. In deterministic methods, we use mathematical functions to calculate the values at unknown locations based either on the degree of similarity or the degree of smoothing in relation with the neighboring data points. So examples are inverse distance weighted radial basis function, and spline function is there. So all these functions you will get in standard GIS software like ArcGIS or QGIS. You can use all these things. The idea is that in deterministic method, a textbook description is given like this. You have input data and you are applying IDW. How many times you are applying IDW? You are applying IDW for the first time, you are applying IDW for the second time, third time, you will get the same result. How many times you run this technique, you will get the same result, because it is a fixed mathematical calculation. It's a fixed mathematical calculation. In geostatistical method, you use probability. You use statistical methods to predict values at all locations within the region of interest, and to provide a probabilistic estimates of the quality of the interpolation based on spatial autocorrelation. We will discuss all these spatial autocorrelation. So the basic difference is that one is a mathematical function. It's like, x plus y is equal to z. So just a formula. So irrespective of the times of repetitions, you will get the same result. But here in statistical methods, it considers the observations, whatever we have seen as pH in the ground. It considers as it is a realization of a probability distribution. It's just like throwing a dice and you see what is the value, and you repeat this. So it is a probability. What is the probability that you will get a value of 5 of throwing this dice? It's just the same way. It treats geostatistical methods treats the geographical variable as a part of, as a realization of a probability distribution. What is the advantage? The moment you use statistical methods, you will be able to estimate the accuracy of it. In the previous case, you won't be able to do it. Here, you can, there are several techniques by which you can try whether your prediction has got good accuracy. Accordingly, you can fine-tune the model and repeat the exercise until you will get a satisfactory accuracy of your prediction. So that is the basic advantage of using a geostatistical method. So Kriging is a very important technique that comes under the geostatistical method. So the rationale behind spatial interpolation is the observation that points close together in space are more likely to have similar values than points far apart. So this has been conveyed as a law, and which is called law of geography. This is proposed by Waldo Tobler. The law says everything is related to everything else, but near things are more related than distant things. So this is the basic premise behind interpolation, and near points generally receive higher weights. So the idea is that in the geostatistical estimation process, we will give higher weightage for points which are closer with the higher values. And suppose if you ignore this, you ignore the spatial dependence, which can lead to erroneous model assumptions, because the weightage which you give for samples which are located near will be different for different geography, will be different for different variable. You cannot use the same variable to estimate. Suppose you are using to estimate rainfall, that will be different from soil nutrient, that will be different from the water quality. So for every variable, for every geographical region, you have to develop this type of a model. Again, this can be further explained by a simple example. That suppose I'm not very sure where your exact location. Suppose in the Adamas campus, suppose it rains. So you have you can fairly confidently say that it might rain in the near vicinity. But a place which is 20 kilometers away from this, you won't be very sure. You won't be very sure whether it is raining or not. You won't be absolutely not sure for a place which is 100 kilometers away from your location. So if you look at, if you think in this sense, you can see that many of earth science and environmental variables can be, what do you call, it can be modeled like this. It has this type of behavior, many characteristics. Another example would be like, say, in a water body, say there is a pond or there is a well which is highly contaminated, either biological or chemical contamination is there. So there will be fairly, there's a fairly good chance that the water bodies in the surrounding areas will also have this quality issue, and it will gradually, it will change only gradually, because the water table will get mixed up. So this way, many variables like pollution, all these variables behave this way. And this is very, very important that whenever, normally we just overlook this. When we get a large data set, especially the people who work in GIS and geoinformatics, the moment you get the data, you just apply it in some map form and do the spatial analysis and get the results. This is I would say this is the flip side of GIS, because the people will get fascinated by the power of visualization, and through which most of the times you overlook the quality of the data, because with few clicks you will get a very nice map. So you will get excited with the map that you keep ignoring some of the data quality issues. So what we can say is, like, you have to do all the data cleaning and data quality verifying techniques before you take the data into the analysis. So for example, the first thing, if it is a numerical data, quantitative data, the first thing you have to do is whether you have to check whether this is a normal data, whether it has some outlier or not, whether it has some skew, the data is skewed or not. So what would you do if the data is not normal? You have to apply some normalization techniques. You have to remove the outliers. You have to look for the missing data. So in one of our projects, we just started with this data cleaning exercise. We found a lot of issues. Like in some cells, some cells will have a value of 0. You are not sure whether that 0 is an observation. That means you collected the sample and did the analysis, you found that it is 0. It can be an instance. Otherwise, the null value, the missing value might have entered as a 0. So that the typo error can come. If it is a manual data entry process, so errors can come, and the repetitions can come. Like there will be numerically similar values. Suppose if you take pH, 5.6 can repeat several times. You cannot do anything. But when you plot it on a map, if you see that you have a location, you have a specific location with specific latitude, longitude value, and the variable, the value of the variable is also the same. That means you have 5 points, one over the other, with the same value. So why do you unnecessarily keep 5 values? Because all x is same, y is same, z is same. And then something happened in one of our exercises, like you have the points displayed in a regular line. Some 20-25 points come in a regular line at a very close interval. So this is again a human error, because somebody might have, when entered the lat longitude coordinate, he might have sometimes deliberately. This was one instance where people wanted to key in deliberately wrong data. So only when you plot this information, you will see that it is wrong, because it has a particular pattern. The data has the instruction given to the data collector was collect the data on a random fashion. You collect data randomly, should not be in a regular pattern. So we saw that the data are collected in a linear fashion with very close intervals. So whoever has done this was trying to manipulate the data. He was trying to increase the number of records without going to the field. That was the intention. So the idea is, before you take the data into analysis, you have to do exploratory data analysis and exploratory spatial data analysis. These two are different. What I said as an example sometime back was exploratory spatial data analysis. You just look at the pattern of distribution, geographical distribution of the data. Whether are they falling outside this? Do they have any clusters, wrong clusters, intentionally wrong clusters? So all these things are part of exploratory spatial data analysis. Exploratory data analysis is visualizing the characteristics of the data using graphical methods, mainly using histograms, box plot, all these things. The idea is you have to clean the data before you take it into the analysis. Extreme values, outlier values, either extremely low or extremely high values, can greatly influence the quality of kriging. So outliers should be eliminated as a thumb rule before you apply kriging or geostatistical analysis. So data transformation, suppose in this case you can see that if the distribution is not normal, you can use logarithmic transformation. This is one just example of this. So the origin of geostatistics or the kriging is, first of all, it's a statistical technique. It is named after Danny Gerards Kriging, a South African mining engineer who presented the ideas in his master's thesis in 1951. And these ideas were later formalized by prominent French mathematician Georges Matron. So the original idea is attributed to Danny Kriging in 1951 in his paper, A Statistical Approach to Some Basic Mine Valuation Problems with Witwatersrand. The motivation for developing this was like he wanted to estimate the mining reserves. So the problem with mining estimation is that you have very few samples, because you cannot afford to have large number of samples. with whatever limited samples in hand, because it involves a bore sample. So you cannot have more samples because it is not collected from the surface. It's collected from the deep inside the earth. So with the very few samples, he wanted to estimate as accurately as possible about the mining reserves. So the technique Kriging is named after this gentleman. So the Kriging has two parts actually: quantification of the spatial structure in the data and the prediction of values at unknown points. So this is, as I said, these are some of the difference between the deterministic approach and the geostatistical approach. So the two parts. First part is quantifying the spatial structure in the data. So this is very interesting that depending on the variable in hand, the spatial structure will be different. So the spatial association of the variables at a place will be different for different contexts. Like it will be different for water quality, it will be different for soil nutrient, it will be different for a plant species, it will be different for air pollution. So first thing we have to do is to study the spatial structure from the collected data, and after studying the spatial structure, use the parameters of the spatial structure as a weightage to be applied in the Kriging. That's the second part of it. So we will see. Basically, it forms weights from surrounding measured values to predict values at unmeasured location. The closest measured values usually have the most influence. We have seen that. Kriging weights come from a semi-videogram developed by considering the spatial structure of the data. To create control surface or map of the phenomenon, predictions are made at location in the study area based on semi-videogram and spatial arrangement of measured values. So the Kriging formula is for a random variable Z measured at sampling locations xi, I is equal to 1 to n. The value of the variable at an unsampled location x0 is estimated by z cap x0 is equal to sigma I to 1 n lambda I z xi. So lambda I are the weights. So these weights will come from the variogram analysis. The foundation of Kriging is known as spatial autocorrelation, or tendency of values of entities closer in space to be related. So here, at this point, we need to discuss this. What is spatial autocorrelation? We all know what is correlation. Correlation is measuring a change in one variable depending on the change of another variables. If you take x and y, how the change in x, how it affects the change in y. So it can be positive correlation, it can be negative correlation. If it is zero, there is no correlation. So when it comes to spatial autocorrelation, we don't have two variables, we have only one variable at hand. But you will take the variable at the first location and the same variable at a neighboring location. So it is separated by a distance. So assume that pH in our previous case, we go back to the QGIS. See, in this case, the variable is same. The variable is soil pH. So if you are taking the spatial autocorrelation, it will consider this point and this point, and this point and this point, this point and this point. It will consider all the all pairs of points, all possible pairs of points. So that is why it is called spatial autocorrelation. How? So the idea is when a value is changing here, how it will affect the values of the surrounding points. So that is why it is called spatial autocorrelation. It is spatially at a distance. It takes the spatial location. So this is a violation of classical statistical models since observations are assumed to be independent. So in normal classical statistics, where you deal with numerical data, not the location data, you assume that the data are independent. Data are independent of the neighboring observations. So it's diametrically opposite. The concept is diametrically opposite. Here it has to be dependent because because of the law of first law of geography. So autocorrelation can be assessed using a semi-variogram, which plots the difference in pairs against their distances. So when you plot this semi-variogram, you will get a graph like this. So this is how it appears in ArcGIS. And these are the clouds. Remember, these points are not the spatial points. These are not the spatial. Don't think that these red dots are spatial points. No, these red dots are semi-variance values calculated using a formula. We will see how this is calculated. So it is called semi-variogram cloud. These are not geographic locations. These are semi-variance values at a lag distance. Semi-variance values calculated at lag distances. So there is a procedure to calculate the distance. You will get a cloud and you will fit a line. So this line, the parameters of this line is used for Kriging. And it has, what are the parameters? The parameters are, the values is called as sill, the sloped area range, and this is nugget. Now I'll tell you, where the graph is meeting the y-axis, this value, 0 to this value is called nugget. And the value at the x-axis at which the curve flattens. See, in 4.02, the curve flattens. So this 4.02 is called sill. When you minus the sill by nugget, so 4.02 minus 1.34 is called partial sill. It's a partial sill. And in x-axis, the distance at which the line flattens or begins to flat is called the range. So what I'm trying to say is that, suppose you do this semi-variogram analysis for one variable, pH, the graph will be like this. And if you do it for potassium, the graph will be different, because the spatial structure of that variable will be different from pH. It will be unique, actually. So if you take phosphorus, you will get a different curve. So this is the first exercise of Kriging. So a quick explanation of autocorrelation. Normally, in the classical statistics, correlation of a variable with itself, the correlation between, the correlation is, in classical statistics, the correlation means how a variable is changing based on another variable. So in autocorrelation, correlation of a variable with itself through space. The correlation between an observation's values on a variable and the value of a close by observations on the same variable. The degree to which characteristics at one location are similar. And there are several measures with which you can estimate the autocorrelation. And these are joint count statistics, Moran's I, Geary's C ratio, Gettysord G, and Anseline's local index of spatial autocorrelation, otherwise called LISA, among which Moran's I is mostly used, which is a global measure of a autocorrelation. That means global means for your entire study area, it will calculate a single measure. And if on the contrary, if you look at LISA, as the word says, it is a local measure. Local measure means instead of taking the whole area, it will take a subset of the area and estimate the autocorrelation, so that you can see how the autocorrelation varies in space. So there will be local variation. So that can also be studied using LISA. One thing to be remembered is, before you apply all this, spatial autocorrelation or Kriging, or before you apply Kriging, with your scientific knowledge, you have to check whether the data can be subjected for this analysis. What I'm trying to say is that only if the variable is spatially autocorrelated, only then you will be able to apply Kriging. If the variable is not spatially autocorrelated, Kriging will end up in wrong exercise. It will give wrong results. I'll give an example. Now, we have discussed about what do you say, soil nutrient or soil property or elevation or presence of some bacteria in soil, such as nematodes or something. These are all spatially autocorrelated. That means if you have a high concentration there, you can assume that the neighboring areas will get affected by this. But there are certain other variables which are not spatially autocorrelated. For example, if you take some socio-economic aspects like the per capita expenditure of households, you cannot say that it is spatially autocorrelated. You can't say that if a group of people residing in one area spends too much, then the surrounding areas will also get influenced by this. So you cannot say that. The same way some, for example, lifestyle diseases like diabetes. If there is a cluster of people with diabetes, you cannot say that the neighboring areas will also tend to get this. But if it is a communicable disease like dengue fever or COVID, you can apply spatial autocorrelation. So before you start the Kriging process, you have to make sure that only if the variable is complying with the spatial autocorrelation or complying with first law of geography, only then you attempt to do the Kriging. Now, as we already discussed, the first step of Kriging is studying the spatial structure in the data. This is done by SemiVideogram Study, and SemiVideogram is a statistical technique. The formula is 0.5 because there's a divided by 2n, 0.5 average, sigma I is equal to 1 to n, z of xi minus z of xi plus h the whole square. The idea is xi is the variable at one location, and z is a variable. Zxi is the value of that variable at xith location minus the same variable at a separated by a lag distance. H is the lag distance. So if it is located in one point, the h may be say 500 meters. So the same variable at a 500 meters apart, what is the value of that? So you take the minus, you square it, plus you go to the next pair, and you go to the next pair. You repeat this exercise for all possible pairs of points, sum it, divided by 2n, and then you plot the gamma h value. You plot in a graph. So you then the next thing involves fitting a variogram model. After you plot the cloud, as we saw here, let me explain once again. When you do this, when you calculate this formula, what you will get is these points. These points you will get when you do that formula. And after you get this cloud, you have to fit this line. You are fitting the line. So these clouds are called theoretical variogram, and this blue line is called experimental variogram. Theoretical variogram and fit experimental variogram. The theoretical, it's very easy to remember, because theoretical variogram you will get as a theory, and experimental variogram you are experimenting. This is our job to fit this line. We have to fit this line. In fact, this is the concept actually. Fitting the line is a manual method. But in our case, you don't have to do this, because the software itself will fit this line, and if you want, you can modify it. There's an option in geostatistical analysis. If you want, you can modify the line. But in other, if you're doing any programming, scripting languages like R or Python, there also there's a manner in which you can do it. Auto fitting is there, automatically fitting the curve is there. But it is always better, at least at the learning point of time, it is always better to try it out manually, because you will know what is happening. Every time you change the graph fitting, you can see how the output is getting changed. So it's very exciting. You can literally play with it. So as we explained, this is nugget, this is sill, this is range, and this is the gamma h value, like this. So there is also a technique called binning, because what happens is, what is the need for binning? I'll explain here. See, suppose you are trying to calculate the semi-variance. So how does it do? It will start from here. It will take this pair first. That means 5.81 minus 5.23 the whole square plus 5.81 minus 5.99 the whole square, and it will do like this, divided by 2 into the total number. Now what will happen is, if you look at the formula, see, gamma within bracket h is there. That means you have to apply this formula for a specified intervals. That means if you start with say 500 meters, gamma 500, then you have to consider all the pairs of points that are separated by 500 meters. Then arrive at gamma 500. Then the next step, you may go for gamma 1000. Then you have to take all the pairs of distance that fall within a band of 1000. So this is called binning. Binning based on the lag distance. Now, when I show you another slide, you will get it more clear. Look at this. Now, for demonstration purpose, this is taken from a book. I'll give the reference of the book. Let us assume that this is taken at a regular samples. As I said in the beginning, it is a totally ideal situation. Taking samples at regular intervals is a totally ideal situation. You will take samples at random locations only. But just for the demonstration purpose, I've taken this chart. So let us assume that we have collected data at 100 meters. We have observations at 100 meter interval, 44. There is one data missing, 40, 42, 40, 39, and here also 40. And what you will do, you will take the pairs of observations at 100 meter interval. So you will take these two. You are not taking this 44 because you don't have the value here. So 40, 42. You are taking this pair, then 42, 40 you are taking, then 40, 39 you are taking, then 39, 37, 37, 36. Now you apply this formula. When h is 100, you are taking the pairs of points separated by 100 meters. So 40 minus 42 the whole square, because there was a sigma there. 42 minus 40 the whole square. 40 minus 39 the whole square until you reach here 30 minus 32 divided by 2 into 36, because you have total 36 observations. So 2 into 36 divided by 2n. What you are getting is the semi-variance value for 100 meter lag distance. Similarly, you have to proceed with 200 meter, gamma 200. So you will take every alternate points. See here, every alternate points you will take. Instead of 40, 42, you take 44 and 40, 40 and 40. Yeah, that way you take at 200. So you will get a value here, 3.30. And you repeat this, 200, and then you take 300, then you take 400. So it will reach a time when you can see that the variance, the difference between the first point and the second pair of points will be very minimal as the distance increases. So initially it will be very strong. The difference will be very strong. And as you increase the lag distance, you will get the spatial dependence will get weaker and weaker. The difference will be minimal. That's what it will happen if it is an autocorrelated variable. The difference will become minimal. So that is the point where the graph is going to flatten. What is our job? Actually, we want to study all these parameters at what distance it is getting flattened, at what value the graph is going to hit the x-axis, at what sill value this is going to get flattened. So once you get these parameters, so then you can go for estimation, because this is the way that particular variable behaves in that particular locality. So once you get this numerical weightage, this weightage can be applied to the whole data and then estimate for the whole area. So one second. So at this point, should I, is there any doubts? Is it okay?
It seems, sir.
It's okay, right?
Yeah, you continue, please.
Okay. Now, yeah. Now, when we think of fitting the curve, we talked about fitting a curve here. So when it comes to fitting the curve, there are different, types of curves, like spherical, Gaussian, exponential, linear, power graphs are there. So there is, so you can see that if the no sill. So this is if you get a graph like this, it means that there's no spatial structure. So the spherical, Gaussian, all these are will tend to give a good spatial structure with the data. And this is also when you do it, you can try out different types of models, and then you can see which one is best fitting the point cloud, the semivariance cloud. So with this we have already discussed. We can then use a scatter plot of predicted versus actual values to see the extent to which our model actually predicts a value. Then like this, so the bandwidth, the maximum value of h, we can see that if there are n points, the number of interpoint distances is equal to n into n minus 1 divided by 2. That many pairs of distances will be there. Say for example, if we have 15 points, then we have 15 into 15 minus 1 divided by 2, 105 interpoint distances. Like how do we do that? We will, it's like a confusion matrix. We create a confusion 1, 2, 3, 4 up to 15, here also up to 15, and all these diagonal values will be 0, and then you can see the distance between the pairs. Now let's quickly see an example in the slide. So we have, I'll give a demonstration. We have a district, it's called Wayanad. You must be knowing this district. It's a scenically very beautiful district, which is part of a plateau actually. The whole district is in a plateau, and which has a mild, climate, and it is little elevated, almost 1,000, above 1,000 meters from mean sea level. The whole district is it's like a table structure, and lot of it has got tourism important. This thing, a lot of spice cultivation is there. It has got a lot of terraced paddy fields also there. Some of the indigenous varieties of rice, which we have only is cultivated only in this district, with that rice with some natural fragrance. Is little costly, but all these types of crops can only be cultivated in that type of topographic and weather conditions. So in this district also we are facing a lot of agricultural problems, like a lot of soil erosion, and then couple of years back there was a disturbing news that suddenly all the earthworms present in the soil started dying in a very large number. So that means the ecosystem of the soil is getting disturbed, and it gradually affected the agriculture yield and several other issues. So this is the district, and we have soil data pertaining to all these nutrients: pH, organic carbon, phosphorus, potassium, zinc, iron, copper, manganese, boron, sulfur. And we took soil organic carbon as an example, and this is a summary of exploratory data. We have, the box plot and the histogram. We have a lot of outliers, and these are the sample locations. It's a huge data, almost 20,000 or something observations. These are actually points, but when the points are very close together, it appears like a patch. So these are all points actually. So from this, after videogram analysis, so this is how we do it: ordinary Kriging. Yeah, there's 19,272 observations, and yeah. Now we discussed about all the concepts. Now, ultimately, we would like to see this as in the form of a map. So how do we do that? We will create a prediction grid. So this is also very important in Kriging. You will create a prediction grid at a desired interval. This is, the user can decide whether you want it in 100-meter interval or 200-meter interval. You can decide. There are a lot of GIS software or in R or Python, you can create this grid. And after studying the spatial structure of a particular variable, you will create the weightage. You will do the best fitting. You will do the semi-variogram analysis. You will do the theoretical curve fitting, and from the curve fitting, you will use that particular model and apply the prediction over this grid. So what will happen? Each of these values will derive an estimated value of a nutrient. You can easily translate that into a map, so that you can have seamless data available for you. On an advanced level, you can also use regression Kriging, in which in this Kriging, this is univariate. Univariate means you are considering only one variable. Here, what you can do, this can be the variable in interest, can be the dependent variable, and you can consider a lot of independent variables and see how this is affecting the variable. Then you can do the prediction. For example, if it is say nitrogen or organic carbon or potassium in the soil, then you can use maybe the topography, NDVI, land surface temperature, drainage density, slope, all these factors as independent variables, and then you can use the regression. Normally, the accuracy of the regression Kriging will be better than ordinary Kriging, because you are also considering the certain controlling factors, controlling environmental factors. So it will have some improved estimation accuracy. So this is how we got this organic carbon estimation. You can see that it ranges from less than 0.5 and above 3.5 up to 3.5, and then all these metadata, details of what is the model parameters, and we can estimate the accuracy, mean error, root mean error, mean absolute error, RMAE, MSE, RMSE, RMSE. VIII is something correspond to R squared value. So all these can be along with this semi-variogram graph. So I'll just quickly go to the demonstration. So a couple of ways you can do it in QGIS. So we have, let's check how many data are there. So we have 259 observations. We have all these columns: pH, electrical conductivity, organic carbon, phosphorus, potassium, calcium, magnesium, sulfur, zinc, boron, iron, copper, manganese. And then we have XY value as UTM coordinates. Now, in fact, this is a CSV file which I have plotted as a delimited text file, and I'll save it as a QGIS project before doing this analysis. And we have a plugin called Smart Map. So the input layer is soil, the input variable is pH. We are importing the data. And then, so this will give the pH Moran psi 0.1, even though it is weak. This is a weak, weakly correlated, weakly autocorrelated, but it's positive. The value is positive. And we will proceed to interpolation. And you see that the maximum distance and the lag h, it automatically calculates. So you have this curve fitted, and if you want to change the model, you can change it. This actually is it will depend person to person. If I feel that spherical is good, and so CO is the nugget, 0.23 something is the nugget value. CO plus C is the partial cell. Partial cell CO plus C at 0.289, it gets flattened, and A range is 5783. At 5783, the graph is getting flattened. And then all you have to do is just click interpolate. But it might take some time. So what we will do, let it happen. So it will take some time. By the way, I'll tell later that this particular plugin also gives an option to use machine language. I mean machine learning. Machine learning can also be used. But are you aware of machine learning? Does it need a quick, very brief explanation? How about?
They have the
learning?
basic idea. They might
Okay.
have the basic idea.
Okay. So here the possibility of using machine learning is that, see, when you use machine learning, there are two types of machine learning. One is for classification, the other one is for regression. So in this particular case, we have since we are dealing with numerical data, our numerical prediction, our interest will be mostly on the regression machine learning techniques, such as random forest. There are several other algorithms, machine learning algorithms. So the idea is, it's very interesting. Suppose you have 250 points, 250 locations. You have X and you have Y and a variable value, pH or boron or calcium or something. Then for the same locations, you try to get values for independent variables also. Like what is the elevation? What is the slope there? What is the drainage density there? What is the flow accumulation there? What is the soil texture? So you are building actually your regression. So there will be, if there are n, if n is equal to 259, you will have 259 dependent variable, that is pH, and you will have independent variables. What are the factors that are affecting this? So if you give this data, with this data, you can develop a machine learning algorithm, and then using the same prediction grid, you can use the prediction grid to estimate Because in the prediction grid, you will have independent variables. You will not have dependent variable because that dependent variable you have not collected. Dependent variable, you have only got 259 points. Your prediction grid may be 10,000 because you're going to predict for the entire study area. From the 259 points, you will generate a model, and with the model, you will apply it to the prediction grid. But make sure that at the prediction grid, you have each location, you have independent variables tagged to it. Only missing point will be the dependent variable, which you will predict from the machine learning. So that is, so, if you look at literature, most of the literature using machine learning in the context of geospatial, you will find that it is applied using remote sensing data. And mostly it will be classification. The context will be for classification. But here it opens up a large potential of doing the regression estimation, so that what is the difference? What is the basic difference? Instead of predicting, suppose if you are using classification for classification machine learning algorithm for predicting a nutrient, it would tell that this patch you have got high, this patch it has got medium, this patch it has got low. It will be categorical. Whereas if you are using regression machine learning algorithms, it will tell you at this particular location, this will be the predicted value. So that is the basic difference. So now the estimation is almost complete. Yeah, we will come back. We will not waste time. In the meantime, we will see how this is implemented in R. So we'll start with loading the libraries. I am setting the working directory. I have the data here as a soil CSV file, which we have already seen here. So this is the file I'm going to use here. I'm reading the data. Summary data frame. So this is a data frame now. Summary data frame. It gives all the summary of the variables. We have got point X and Y as UTM coordinates. Then what are the names of the columns? And so I'm going to do interpolation for the pH, soil pH. So data frame, within that column name, start with histogram. But luckily it is a normal distribution. This will be a rare case, most of the time you won't have this normal distribution. It will be the highest bar will be on left side or right side. Then you have to try with removing the outliers, and then you may have to do some transformation. So box plot, there is an outlier. See, this 3.970, mean is 5.463, maximum is 6.640. So there's some value below 4. That is an outlier. We have to remove that. So what I'm doing, I'm applying a filter. I would say that for this exercise, I want to use values which are above 4, because I have only outlier as on the low end. We don't have an outlier on the higher end. So if there is a higher end, I'll have to use ampersand and symbol and then give the condition. So it's only one side. So I'm going to take on values which are above 4. And after that, let's do the box plot once again. It should have vanished. Yeah, it's gone. Now what I'm going to do is I'm going to convert this as a geodata. See, in geodata, there's several ways in which you can convert this as a geographical data. You can use binding. You can coordinate bind. If you bind the coordinates, it will automatically become the spatial points data frame. But here I'm using geodata. Why? Because if you look at this, geodata will have only one attribute associated with it. It won't have multiple attributes. That's what I want it for, at least for this thing. There's no hard and fast rule. If it is a shapefile directly loaded into R, then only you can do this. But for this example, I'm just using the geodata so that it has only one attribute. So how I'm going to do this? Because in the list of columns, I'm taking 14 and 15. 14 and 15 as the x and y coordinates, and column number 1 as the variable. And I'm assigning the soil pH to a variable so that I can use it in my graph. And now I am going to create a variogram cloud. First, it's first creating a variogram cloud. Then I am plotting it. So this is the cloud I'll get. You can see that this is in x-axis. It's in meters, and these are the semi-variance values generated at lag distances. Then now I have to fit the line. So by carefully looking at the graph, I will try with different values. See, the model which I'm going to use is spherical, and Inico parameter. These are the parameters. This I've given here the usage. I have to first give the partial cell. This is the partial cell. That means the partial cell means from the nugget to cell. When you construct a graph, this graph will hit a point in the x-axis. From that point to gamma values at which is getting flattened. So this is the range at what distance it is getting flattened, and what is the nugget value. Nugget value I'm going to 0.1, and I'm saying that fixed nugget is false. That means I give the freedom to the software. This is not hard and fast. I don't want the nugget to be 0.1 exactly. If the graph, when the graph is taking partial cell and the range, it may not hit this point in true sense. It may be a little higher or that. So that freedom I'm giving to the software. So a model is fitted, and then I want to construct the lines. So I'll get a line like this. I can play with that. If I change this line, I can literally play with that. And then this has been stored in a variable. The parameters of the graph is stored as a variable. So these are the variable parameters. Now what I'm going to do is, at the time of Kriging, I will use this model as the weightage. Before that, I'll have to construct a grid, a prediction grid. Prediction grid is required because that is where the predictions are made. Now, how do I do that? How do I get the prediction grid? Requires, min x, min y, and the number of columns, number of cells, and min x, max x, and number of columns. So this is very easy. And if you go to the QGIS, and yeah, you got the prediction here. QGIS has predicted this, and you know that when you load a layer in QGIS or ArcGIS, if you go to the metadata, you will get the bounding extent. So from the bounding extent, I have taken this values, and I'll give the difference. How many columns are required, how many rows and columns are required to draw this. So the idea is, when you give 205 and 433, it should be, because this particular, the shape of the panchayat, if you remember, it has got higher length and shorter width. That is why it is coming like this, 205 and 433. And I'm plotting it. So it's a very dense point cloud. Oh my God, it's okay. Leave it. Let's continue with this. Yeah, it has come. So if you zoom it, so I've used too many points, prediction grids. Now, what I'm going to do is using the Krig dot conversion. This is where I'm going to predict it. So I'll give the source data, which coordinates I'm going to use, and which data, because when I use soil dollar data, there's only one column. And then I'm using the prediction grid. See here, covariance model. Here I'm going to use fit dollar covariance model. This details are taken from this model. This is where it is taking the parameters of the model. So I'm going to predict this. By virtue, prediction grid is not a spatial data. It is just a matrix data. So I have to use the data as well as the coordinates. I'm going to bind this because I want it as a map. I'm going to use 32643 UTM 43 north coordinate. I mean CRS. I'm just making sure that this is UTM 43 north, and then once a spatial point data frame is created, I have to make it into a raster data. So I've got the prediction here. So you can see that pH ranges from 5.3 to 5.7. These are the values. These are the places where you have low pH values, and the green shows the patches with high pH value. And if you have a boundary file as a shapefile, because this is this always uses the prediction grid. You know, in prediction grid, we have used the bounding extent of the data. In fact, our boundary may be within this. So how do we know that? So this is the boundary. So the data outside this boundary is actually will have erroneous data because it is extrapolation, because you have data for this area. So I just want to create a mask, and then do the estimation only for this. And you can always save this file as a TIFF file so that you can use it in QGIS or ArcGIS, whatever. So you'll get as a raster data. Now the idea is yeah, there's also one more thing, like we can see the error. You can, the same way you can plot the Kriging error, and you can see that all these are deviations from the predictions. Here, what is the idea here is, like, you know, see, now we have got the prediction. You have got the range here, the prediction is there. Now, let me take this. So here the idea is the color denotes the prediction of the pH. And you can see that for every point, every location, it is possible to capture the predicted value for each location. Now we have 259 input points. For these 259 points, it is possible to capture the prediction data also. I mean, in fact, it was there in the see this is it predicted. So from this chart, it see this. The idea is you will get a matrix of 259 points, and 1 point we discarded because it was having 3.970. So we give a filter point there, and this you have observed value and the corresponding predicted value. Now this allows us to do the cross validation. That means how the cross validation is done. Here the cross validation technique is leave one out. That means you have 259 points and 1 point is deliberately removed for the analysis. 1 point is not used for the analysis. So it does with 258 points, and then for the removed location, it will identify what is the value here. You have a observation value and you have a predicted value, which is not used for the prediction. The same way, you can have 259 set of points with observed and predicted. Once you have a matrix of observed and predicted, you can easily do the cross validation like the RMSE, RSC, I mean root R squared. All these can be done. So the idea is, this is actually, if you look at the R squared, it's not a good value. That means you have to fine tune this. You have to go back and fine tune this until you get a better R squared value. You can, you have to keep doing the fine tuning exercises so that you will get a very nice prediction as well as good accuracy, with a good accuracy. So this is what we said in the beginning, that this playing around is not possible with IDW because you cannot because it's not a probability distribution. It's not a probability distribution. So this gives the flexibility of fine-tuning the parameters and coming out with better accuracy and better interpolation. So that is all from my side, and may I take some questions?
Yes, sir. We have 2 questions in the chat box.
Yeah, I'll go through it.
Okay.
What is the relationship between, oh my God, what is this? Stilton-Bose method and Sten-T-Gears method. This is from machine learning.
I don't know. I think from choropleth isopleth mapping. These methods are related to isoplating or choroplating. I guess so. I'm not also very sure.
No, I'm also not sure about this. Okay. Maybe this is from cartographic.
Yeah,
it's a cartographic method.
Yeah. Yeah. We can have another question from our student Shinchan, who said that what is the difference between Kriging and IDW, but I think sir has already explained this thing in the first slide. But if sir wants to explain it in more detail.
Yeah, IDW is a mathematical technique. That means it does not consider the probability distribution. It does not consider the variable as a part of probability distribution at all. It just applies the inverse of distance as a weightage. It uses inverse of the distance as a weightage. That means closer points will have higher weightage, and if the distance is close, weightage will be high. So that is why it inverse. It applies that as for calculating for estimating the values at unsampled location. It does not, in nutshell, the basic difference is that it does not use the spatial structure, spatial dependence in the estimation process. First difference. The second difference is that it does not produce an error map. That means, see, here we have observation as well as predicted. So this can be used for estimating the accuracy. In IDW, it is not possible because every time it gives only one single output for a estimation process.
Okay. Okay, sir, I have one question and then we will take
Yeah.
Dr. Rai's question as well. You have said that before applying Kriging, we have to understand whether they are specially autocorrelated or not by
Yes.
themselves. So the process you have shown us in QGIS, it automatically runs the spatial autocorrelation first and then we go for this. So there is no
Yeah.
separate requirement for this.
No, no, no. There is no
Okay,
separate requirement.
okay, okay.
But
Okay, thank
you have to always see the strength of spatial autocorrelation before doing it with
okay.
Kriging.
Yeah.
So there's another question.
Yes.
Can you just highlight once again when we need to avoid application of Kriging method? See, this is based on number one, our scientific knowledge, using which you have to see whether a variable in one location, will it affect the variable in the surrounding location? This is based on our scientific knowledge. If you feel that you cannot spatially autocorrelate the variable, then you cannot proceed with Kriging. Basically, some of the parameters like we have seen, like per capita expenditure or lifestyle diseases. So all these habitual things and some examples, some other examples, if you feel that is not spatial autocorrelate. So first thing you have to check is whether the variable is spatially autocorrelated or not. Only then you can proceed with Kriging.
Okay, thank you, sir. So can I add? Can I ask one more extra question, like
Yeah, please.
something related to application? So you said that we need to avoid this habitual, means like the per capita income or the habitual activities which are not spatially autocorrelated, maybe. But from the tourism perspective, if we can see, like suppose like I have a data from the Northeast India, we have surveyed patients who are coming to Kolkata, and in total we have 312 samples. Now those 312 patients are coming from the 8 different states of the Northeast India, and we also recorded their zip location, their address of their Northeast places. So when I created a special point of those locations, we have seen a very good clusters of those points. Like the tourists are coming from the specific. In fact, some places like some small mohallas or the localities are very common from where the patients have come throughout, like in our survey of 2 years. So we cannot say that it's the same train or same flight they're using, they're coming and we are getting surveyed. So in entire 2 years of span, we got a very good spatial autocorrelation among those patients who are coming from the 8 different states of the Northeast India. So here, like when I run the global Moran-SAI, like I got very good spatial autocorrelation results. It's very good. But I feel like whether if I'll run the Kriging method to check the means this. I want to run the spatial dependence model here. Actually, I want to see whether am I able to do that? I mean, is it correct or statistically I'm getting very good result actually?
Yeah, it's a very good use case. Actually, I would say like this. There is a spatial clustering is there. That means it is autocorrelated. At the same time, that clustering is a result of some other variables, like maybe a tourist important place is there. That's why the people are coming in. But you cannot do it. You cannot go ahead with Kriging because you cannot say that. See, at this location you have a cluster, and in another location you have a cluster. That cluster is there, or the cluster is manifested because of some other reason. You cannot say that since there is a high cluster and there is another cluster, in between you can have a estimated value of tourists. You cannot say that.
Exactly.
That's not possible. So in such cases, you cannot proceed with Kriging because there's no, there won't be any meaning for that. You cannot say that in this particular area, the estimated tourism concentration or intensity is this because of you have few clusters there. Instead, I would say like you can proceed with some density analysis or clustering analysis, and then you can try to see the attributes. What are the attributes that contribute to the cluster? Something like Getty sort, Getty sort or
Yes, sir. Like we got very good result of the Getty sorts and also the Lisa, because the local clustering is very important there. So we have surveyed, so we got to know that basically they all are influenced by a particular group of the doctors, like who are referring them to visit these places. Like Kolkata, we have surveyed at Kolkata and Vellore. So we got the same clusters from the same locations. The patients are moving from to Kolkata also, to Vellore also. So the basic reason, that we understand from the discussion, it is basically related to the referral points of the doctor. The same doctor is referring, like you could go to Kolkata, you go to Vellore. So just trying to identify whether we can correlate it with the special factors or not. Thank you very much, sir. Thank you very much, sir.
So one thing we have to remember is that the purpose of Kriging is to estimate the variable, estimate at an ensemble location. So we have to decide on that factor first. Is it possible or is it meaningful to predict the variable at an ensemble location for a given situation? So
True,
that decides the factor. That decides the consequent factors.
Thank you, sir.
Thank you, sir. Dr. Rajiv Sharkar.
Yeah, thank you, sir. Thank you for your nice presentation. My question is, can you just elaborate some of the facts about the empirical Bayesian Kriging? Because when we can use it and what scale? Empirical Bayesian Kriging. Empirical Bayesian Kriging. Empirical Bayesian.
Bayesian. Yeah, very good. Oh, good. This is an excellent question. See, for example, I'll give with an example. In ArcGIS has already introduced this Bayesian Kriging technique. What it does is, instead of manually fitting a curve, what the software does, it will have, say, 100 or more than 100 curve fittings on a random basis. It will repeat it and it will take a best parameters out of that. So this is nothing but, instead of this is an automating process. This is an automating process. It will keep trying out with different parameters randomly, different with a band, with a lower end and higher end band. It will keep doing it. So, for example, in geostatistical analysis, the curve fitting will be running for 100 or more than 100 times, and it will come out with the best fit one. So it is expected to have more accuracy than manual fitting.
Another question is that, sir, we in Kriging and in geostatistical part, we have seen that trend has a great impact, and direction and trend. So how we can actually remove these factors of trend in this Kriging point of view, and what are the intricate factors in trend in Kriging analysis?
Yes. In fact, I have not gone into the details because of the constraint of the time. There are, in fact, different types of Kriging, like ordinary Kriging, simple Kriging, universal Kriging, Kriging with a drift, co-Kriging is there. Another technique is like, if you feel that, or if you have observed that there is a direction in which the change is more, or in some other direction the change is less. What you can do is, what we have done, what I have demonstrated is an isotropic Kriging. So in anisotropic Kriging, you can also consider the direction. You can try out different directions. You can input the angle. Remember the graph I have shown, taking consecutive values. So if I don't specify the angles, it will run for 360 degrees. It will take all the directions. If I specify angles like 45 degree, 90 degree, 160 degree, then it will run. The variogram will run only in that direction and try to pick out the spatial structure in a linear fashion. So if your data is exhibiting some linear patterns, then it is suggested to use anisotropic Kriging.
Okay.
Thank you, sir. Thank you very much.
Yeah, Dr. Ahmed. Yes, Dr. Nehal Ahmed. Yes, sir.
Good afternoon, everyone.
Yeah, good afternoon, sir.
And a lot of thanks for your conceptual lecture, Radhakrishnan sir. Of course, this is the more beneficial for everyone. But my question is that here, sir, a statistical and quantitative method cannot be accepted in some cases, sir, as a means for the interpretation of geographical relatives, because empirical methods like emotion, impulse, beliefs, fear, or desire, etc. And in such a situation, how can we accept better and accurate result for this method, sir?
Yeah, first of all, all these techniques are quantitative techniques. All these techniques are quantitative estimations. And when it comes to the behavioral or qualitative aspects, most of the cases, those who work with machine learning may agree with me that the normal practice is that you give some ranking to this and convert this into some numerical form before going with analysis. But even then, these techniques are used in machine learning. Say, for example, in machine learning, when you get some 20 independent variables, some of the variables may be categorical variable, not numerical variable. So in such cases, you give a kind of ranking for this. Again, but if you're using some univariate analysis, the Kriging is not recommended in behavioral interpolations. That's not, Kriging is not recommended. In such cases, you can use machine learning techniques.
Okay. Yeah.
Thank you
a
so
lot.
much, sir. Thank you.
Thank you, sir. Another question is in the chat box. So this will be the last question for today's session.
Could you please explain the calibration and validation part of Kriging interpolation? Yeah, this is very straightforward. When you do the Kriging, as I said earlier, cross-validation is the main technique used, because when n number of points are input into the system, it will create n number of predictions. So you have observation and you have predictions. From this, you can very easily do the validation parameters like mean standard error, R squared, RMSE, all these can be calculated.
Okay. And sir, what is co-Kriging? Shinchan asked.
Yeah, co-Kriging is like, when in some cases you have a variable in consideration, but that variable has got very minimal number of observations. You have very few. You cannot use it. It is so less that you cannot use it for Kriging. In such cases, what you will do, you will find out another variable which is closely related with this past variable, but that variable you have got enough number. Okay, so this relationship between variable A and B, where you want to Krig A, but the number of A is very less. But there's a very strong correlation between A and B. So this relation, you will use B. It's like, fooling the system. You'll try to estimate B. From the estimation of B, you will come back to A because of the cross relation, because you have very minimal number of variable in hand. In some of the literature, there is a book called Basic Variogram Analysis book. In that book, it says that for a reasonably good Kriging analysis, you would require minimum 150 observations. So I have seen many people do the Kriging with 10 points and 15 points. So this literature says that it is good to have minimum 150 points for doing the Kriging.
Okay. Okay. So that's all. You have answered all the questions, and I cannot thank you enough for making such a lucid and important presentation, important in terms of our usage, that we use interpolation in almost every kind of work that we do in geospatial platforms. So it's very pertinent topic that you have talked about, and it was a wonderful lecture. Thank you so much. So
thank you so much. Thank you very much for this opportunity.
Thank you all the students. Thank you my colleagues. Thank you, sir. So have a nice day. Thanks a lot.